Okay, so you've sent us a really fascinating puzzle today.
Mhm.
It's this collection of diagrams, some descriptions, even calculations.
Yeah, all about building structures.
Specifically homes, right? And focusing in on, well, the roofs above us.
That's the core of it.
So our mission for this deep dive, really, is to pull out the essential stuff, what holds a house together.
Especially that roof.
Exactly, and make it, click for you listening. Have you ever stared up at a roof line, maybe, and wondered about the hidden engineering?
What's keeping it strong?
Yeah, against wind, rain, all of that.
Yeah.
Let's dig in.
Well, what's interesting when you look at any building, especially a house, is you can sort of understand its strength by looking at its layers.
The layers, okay.
Starting right from the ground up, your sources definitely highlight this.
Right. And our building.pdf source, it talks about the substructure. Now, this isn't the flashy part, is it?
No, not at all. It's kind of the unsung hero working away underground.
Okay.
The substructure is basically the building's foundation, everything below ground level.
So what does that include specifically?
The key things are the foundation itself and the footing. You can think of the footing as this wider base, like a foot spread out, sitting right on the soil.
Ah, okay.
And then the foundation connects that footing up to the rest of the building. It anchors it.
So it's a bit like tree roots spreading out for stability. Is that a fair comparison?
That's a good way to think about it, yeah.
Uh.
And its main job is,
Mm-hmm.
its fundamental role is just to bear the weight, all the weight from the building above it that's called the superstructure,
Right.
and transfer that load safely down into the ground. A solid substructure is, well, it's non-negotiable. It's the starting point.
Makes total sense. And yeah, that's the part we generally don't see.
Right.
So what about the part that actually, creates our living spaces? That's the superstructure you mentioned.
That's one. The superstructure is everything you do see, everything above ground.
Okay, so that includes...
Well, the obvious things. The walls that make the rooms.
Mm-hmm.
The windows bringing in light, the floors you walk on, and really importantly, the framing that holds up the roof.
So those walls aren't just dividers. They're actually part of the support structure leading up towards the roof.
Exactly. They bear load too.
Which brings us neatly to, well, often the most visually distinct part, the roof.
And the sources really emphasize that, especially with roofs, we're often talking about a framed structure.
Framed, what does that mean in this context?
It just means the roof relies on a kind of skeleton, a framework, often called a roof frame, or maybe a roof truss,
Right.
made up of interconnected pieces, members. And this frame is what gives the roof its shape
Uh-huh.
and provides the strong base for the outer covering, the stuff that keeps the weather out.
Okay, and a really common type of this framed roof one you see everywhere is the gable roof. Figure 7 in our materials shows this pretty clearly.
Yeah, it's classic.
How would you describe it simply?
Imagine a pitched roof. So it's sloped, right? With two sloping sides meeting at a high point in the middle.
The peak.
The peak, or the ridge, exactly. And at each end, you get that triangular shape. That's the gable end.
Simple, effective. Let's rain and snow slide off.
Pretty much, yeah.
Now, figure 7 gives us some actual numbers for a specific gable roof design. It says the span, so the width, is 60-70 millimeters.
Okay.
The length, like along the ridge, is 900 and 144 millimeters.
Mm-hmm.
And the rise, that's the vertical height from the wall top to the ridge, is 1,220 millimeters.
Right. Those define the basic geometry.
So what are the key parts, the structural members, holding this specific roof up? We hear about rafters.
Absolutely. Rafters are, you could say, the backbone. In this design, they're spaced 609 millimeters apart.
Okay.
And they're the main diagonal support. They run from that ridge down to the top of the walls.
But they don't work in isolation, do they?
No, definitely not. There were other crucial members tying it all together.
Yeah.
The sources actually point out 4 other key ones for this kind of roof.
All right, let's break those down. What else is essential up there?
Okay, first you've got the ridge board.
Ridge board?
Yeah, it's a horizontal beam running right along the very peak, the ridge. It's where the tops of the rafters meet.
Okay, and its job is?
Think of it like a central spine.
Wait.
It helps keep all the rafters lined up properly
Alignment.
and
Right.
gives them a solid surface to fix to at the top.
So kind of like the keystone in an arch, maybe? Helping lock it together?
That's actually a pretty good analogy, yeah. Helps distribute the load, too.
Okay, what's next?
Next up, the purlin. Now, a purlin isn't at the very peak like the ridge board.
Right.
It's another horizontal beam, but it runs underneath the rafters, supporting them somewhere along their length, usually mid-span.
Ah, so it stops them sagging in the middle.
Exactly. It adds extra strength, prevents bowing,
Yeah.
especially if you got heavy tiles or snow load.
Got it. Mid-support, what's number 3?
That would be the wall plate. This is a really important one. It's a sturdy piece of timber fixed right on top of the wall.
Okay, sitting on the brickwork or blockwork?
Usually, yeah. Its job is to provide a solid, level base for the bottom ends of the rafters to connect to.
Right, the landing point.
Exactly. And question 2-3 in the docs actually shows a sketch of how the rafter connects here. Often uses bolts, special nail plates.
So you make sure it's really secure.
Very secure. It's a critical connection.
So wall plate, the link between the vertical walls and the angled roof. Got it. And the last essential member.
That's the collar tie. This is another horizontal piece.
Okay.
But this one connects two opposing rafters somewhere higher up, between the wall plate and the ridge.
Ah, tying them together across the span.
Precisely. Its main function is to stop the rafters from spreading apart at the bottom.
Oh, I see, like under wind load or the weight of the roof itself.
Exactly. Stops the roof pushing the walls outwards. Keeps the triangle shape rigid.
Okay, so ridge board, purlin, wall plate, collar tie, along with the rafters, each playing a specific role.
Makes for a strong, integrated structure.
So how do you actually get one of these rafters into place? It sounds quite precise. Are materials lay out some steps?
Yes, it is precise work. There are basically 6 key steps for installing a rafter correctly. Accuracy is really, really important for the roof strength.
Okay, walk us through that process.
All right, first step, measure and mark the rafter length accurately.
Based on the span and the pitch.
Based on the span of the pitch, yes.
Yeah.
You calculate the exact length needed. Second, you cut something called a birdsmith joint.
Birdsmith.
Yeah, it's a specific notch cut into the underside of the rafter near the bottom end.
Okay, what's that for?
It's shaped so the rafter sits securely and squarely right onto the wall plate, stops it sliding off.
Ah, like a little seat for it, a precision cut.
Exactly. Third step, cut the top end of the rafter. This needs to be angled perfectly to fit snugly against the ridge board.
Right, meeting at the peak.
Fourth, carefully lift and position the rafter. Put the birdsmith onto the wall plate, line up the top end with the ridge board.
Sounds like it needs careful handling, maybe 2 people.
Often, yes, especially for longer rafters. Then, fifth step, and this is vital, temporarily brace the rafter.
Why temporary?
You need to hold it in exactly the right place, keep the alignment perfect while you get ready to fix it permanently. You brace it to adjacent rafters or temporary supports.
Okay, keeps everything straight.
Absolutely. And finally, step 6, secure it. Use nails or screws, properly specified ones, through the joints at both ends.
At the ridge board and at the wall plate.
At the ridge board and through that birdsmith joint into the wall plate. Solid connections.
It really is precision engineering, just with timber.
It absolutely is.
Now, our sources don't just describe this, they also get into the math behind it. There's a calculation for the length of that rafter in Figure 7.
That's right, yeah. Question 5b shows how you can figure out the length of that rafter, member C, using the Pythagorean theorem.
Ah, good old Pythagoras.
Oh!
A plus B equal to C, that's star? From school math.
The very same. Still fundamental in construction.
How does it apply to a roof rafter?
Well, you've got a right-angle triangle, the vertical rise of the roof.
That was 1,220 millimeter.
Right, that forms one side.
Yeah.
And half of the horizontal span.
The span was 70 millimeters, so half is 3 or 35 millimeters.
Exactly. 35 millimeter, that forms the other side. B, the rafter itself is the long side, the hypotenuse C.
Opposite the right angle, okay.
So the calculation runs 1,220 squared plus 385 squared.
Okay, let's see. That comes out as...
Comes out as 10,698,625. Then you find the square root of that number.
Which gives us?
Approximately 270 millimeters, so about 3.27 meters. That's the calculated length of the sloping rafter.
Not counting any overhang, right? Just point to point.
Just the structural length from wall plate line to ridge line, yes. And getting this calculation right is crucial. Ensures the roof slope is correct, ensures everything meets up properly at the ridge.
So basic geometry, but absolutely fundamental for the structure.
Couldn't build it accurately without it.
And it's not just the length of one rafter, is it? We also need to know how many to use.
Correct. And there's a calculation for that, too, for the number of rafters on one side of the roof. It's pretty straightforward in this example.
How does that work?
You take the total length of the roof along the ridge line.
Which was 900 and 144 millimeters.
Right. And you divide that by the spacing between each rafter.
Which was 609 millimeters, center to center.
Exactly. So 944 divided by 609.
That gives 15 exact.
15 rafters needed for one side of this particular roof. Plus, you often add one extra for the end, depending on how you measure. But the calculation gives you the number of spaces, essentially.
Okay, so 15 spaces means 16 rafters usually, or 15 plus the gable end framing.
Something like that, yeah. The key is the spacing is determined by things like the load the roof needs to carry, the strength of the timber.
Got it. So 15 or 16 on one side, same on the other. It's quite a few pieces up there working together.
It's a real team effort, structurally speaking.
Now, all this framing, the rafters, ridgebird, purlins, that's the skeleton. But what about the skin? The bit that actually keeps the rain out?
Ah, yes. The roof coverings, important. Question 2 lists 4 common suitable types.
What have we got?
Well, there are asphalt shingles, very common, especially in North America, cost-effective, easy to install.
Okay.
Then you have clay or concrete tiles, heavier, very durable, great lifespan, nice aesthetic. Think Mediterranean or traditional looks.
Right, I can picture those.
Metal roofing sheets are another option. Strong, lightweight, very weather-resistant. Can be long sheets or tile effect panels.
Becoming more popular, it seems.
They are. And finally, wooden shingles or shakes. Gives that natural, more traditional look. Cedar is common.
So quite a range of choices. Depends on cost, looks, climate.
All of the above.
Yeah.
Durability, weight is a factor too for the structure underneath. Maintenance.
Lots to consider.
Right. Now, Figure 7 showed us that nice, simple gable roof.
Huh.
But the materials also mentioned Figure 2, which looks a bit more complex.
Yes, Figure 2 shows a single-story house, but the roof design is a combination. It has both gable ends and hipped ends.
Hipped ends, what's that? A hipped roof is where all sides slope downwards towards the walls. Instead of a triangular gable end, you get a sort of trapezoidal shape sloping down. More complex framing.
Okay, so Figure 2 mixes those styles.
It looks like it, yeah. A main gable section with hipped ends, perhaps. And another detail mentioned for Figure 2 is the roof overhang.
Overhang.
This is that the roof extends 300 millimeters beyond the outside walls, creates an eave.
Ah, okay. Why do that?
It's really important, actually. Helps protect the walls, windows, even the foundations below from rain runoff and direct sun. Good design practice.
Makes sense. And it gives dimensions for that house, too.
It does. Overall dimensions are 7.3 meters by 5.4 meters. And it gives the total vertical rise for this roof as 1.5 meters.
A bit higher than the first example.
A bit higher, yes. And that rise is used for another rafter calculation they show.
Ah, some more Pythagorean theorem.
Exactly.
Yeah.
For this roof in Figure 2, they use the rise of 1.5 meters and a horizontal run of 3.5 meters.
Where does the 3.5 meters come from?
That would likely be half the span of the main roof section it relates to. So 1.5 squared plus 3.5 squared.
Okay.
Take the square root. And gives a common rafter length of about 3.81 meters for this design.
So different dimensions, maybe a different pitch, but the same mathematical principle applies.
Absolutely. The principles of structure and the geometry remain consistent, even as designs get more complex.
Okay, let's try and tie this all together then. We've sort of journeyed from the hidden foundation, the substructure, up through the walls and floors, the superstructure.
The bit we live in.
And then taken a really close look at the framed roof structure. We've unpacked the parts of a common gable, roof rafters, ridgeboard, purlins, wall plates, collar ties.
All those key members.
And even the step-by-step for putting a rafter in place.
The installation sequence.
We saw how basic geometry, Pythagoras, helps figure out lengths and even how many rafters you need.
Crucial calculations.
And we touched on the roof coverings, the shingles, tiles, metal, and saw that roofs aren't always simple gables.
Lots of variety out there.
So hopefully for you listening, you've now got a much clearer picture, a better sense of that hidden framework that makes a sturdy roof possible over your head.
It's quite intricate when you break it down.
It really is. So thinking about all these fundamental structural bits we've discussed, what other factors, what other crucial things do you think play a really vital role in, say, the long-term stability or resilience of a whole building?
Oh, good question. Beyond just the geometry.
Yeah, what else matters? Maybe the specific materials chosen? Their properties?
Definitely materials. Wood versus steel versus concrete. Huge difference.
Or maybe the environment, climate, wind loads, seismic activity.
Absolutely critical. Designing for local conditions is key. So yeah, materials, environment, maybe even how well it's maintained over time.
Yeah, maintenance is huge. It seems like this is just scratching the surface, really.
It's just the beginning of